Hi, so good morning, everybody. And today we're happy to have Professor Chirikjian as our speaker for today's seminar. So Dr. Chirikjian received an undergraduate degree from Johns Hopkins University in 1988 and a PhD degree from the California Institute of Technology in 1992. So from 1992 to 2021, he served on the faculty of the Department of Mechanical Engineering at Johns Hopkins University, attaining the rank of full professor in 2001. So additionally, from 2004 to 2007, he served as the department chair. So starting in January 2019, so he moved to the National University of Singapore, where he served as head of the Mechanical Engineering Department, where he has hired 14 new professors. So as of January 2024, so he moved to the University of Delaware, so where he is the chair of the Mechanical Engineering Department. So Dr. Chirikjian's research interests include robotics, applications to group theory in state estimation, information theoretical inequalities, and applied mathematics more broadly. So he is a 1993 National Science Foundation Young Investigator and a 1994 Presidential Faculty Fellow. So in 2010, he became a fellow of the IEEE, and from 2014 to 15, he served as a program director for the U.S. National Robotics Initiative, which included responsibilities in the Robotics Intelligence Cluster in the Information and Intelligence Systems Division of SAIS at NSF. So Dr. Chirikjian is the author of more than 250 journal and conference papers, and the primary author for 3 books, including Engineering Applications of Non-Commutative Harmonic Analysis and Stochastic Models, Information Theory, and Lie Groups. So in 2016, an expanded edition of his book was published as a Dover book under a new title, Harmonic Analysis for Engineering and Applied Scientists. So let's welcome our speaker.
A very comprehensive introduction, but I brought a copy of this book as a gift, which I'll give at the end. So you left off the most important thing, though, is I now have a secondary appointment in CIS. Yes, so just to let you know, I can supervise PhD students over here, right?
Right.
Okay. So I do quite a lot of algorithms. And so what I'll do today is a brief overview of old topics, talk about the newest work that I've been involved with, which we call robot imagination. And that's related to some other things. It combines computer vision, motion planning, and affordance-based reasoning, and something that we call affordance learning. So we'll talk about that. But first, I'll talk about old work. So the title here is What Goes Around Comes Around, and there's 2 meanings to this title you'll find in a moment. I started my research career looking at snake-like robots and doing motion planning for snake-like robots. So, and this has become very popular recently in terms of continuum robotics and surgical robotics that can work their way in narrow passages. And we looked at how to use caterpillar-like locomotion waves to manipulate objects and things like this. So this was my PhD thesis. And as mentioned, that was from 1988 to 1992. So that was around the time that the Soviet Union collapsed. And so some work I did at that time was, could we recover satellites from outer space? So here, this is, Union of Soviet Socialist Republics. The P is actually an R, okay? So what goes around comes around. People told me, oh, I shouldn't do that because I would date myself, et cetera. But, the world situation is what it is now as well. So I was the person who was building robots in the sub-basement of the Thomas building at Caltech. And then I became interested in theory. And so looking at continuum models of the backbone of this kind of snake-like robot and using that backbone curve for planning and with margins so that wherever the curve goes, the real robot follows the shape. And so we my advisor and I came up with this term hyper-redundant to describe these kinds of structures. The idea being that it didn't matter what the specific mechanical details of the design was, they all had some kind of backbone. So this has become a very popular area. And in robotics, we care about grabbing things. And so we need to describe rigid body displacements in the plane and in three-dimensional space. And so this is the baby version, the planar version. We can describe motions in the plane, rigid body displacements, using matrices that encode both the rotation angle and the position, X and Y, okay? And if you go from one motion to another, you multiply these so-called homogeneous matrices. And that's an example of a mathematical construct called a Lie group. And so and on the mathematical side of robotics, a number of people look at Lie groups and myself included. And so coming back to these sort of highly articulated robots, if you imagine, so in the robots that I showed, these links here, they can change length. They were actually actuators, okay? So this structure with 30 actuators, if you were to sample each of those states, let's say by 10, then you have 10 to the 30th different configurations of the robot arm. And then for each of those configurations, you can record the position and orientation that the end can reach. So then you get this kind of cloud or crescent-shaped distribution of where the end of the hand or where the end of the arm can reach, where the hand can reach. And so this is actually a probability, you can think of it as a histogram or a probability distribution on a Lie group, on this group of rigid body motions of the plane. And so a lot of what I have to do is analyzing that kind of probability distribution, and that's why the first part of this talk talks about state estimation, from state estimation to the more recent topics. But going through some other old work, you know, whether you're looking at a robot arm with actuators or you're looking at a DNA filament in solution bombarded by Brownian motion, the problem is the same. You want to describe where does the end go relative to the base. And so we've published also in more biological contexts. So if we step back, instead of looking at snake robots, if we say we want to move a mobile robot, okay, here's a kinematic cart robot. It looks like a wheelchair. Those are two wheels on the left and right side. If you tell it to go straight forward and the wheels have noise, then instead of going exactly straight forward, it may veer to the right or veer to the left or take some stochastic path. And so what does that have to do with snake robots? Well, it's basically the same mathematics describes the ensemble of possible places where this kinematic cart can reach. The only difference now, instead of arc length along the backbone curve, we have the time variable, okay? But it's the same mathematics. And we get the same kind of distribution. If the robot intends to go straight forward, but that's corrupted by noise, you get a distribution. With the snake robots, we called it the crescent distribution. In the simultaneous localization and mapping literature, they call it the banana distribution, but it's the same thing, okay? And so we wrote a paper saying, well, the banana distribution is Gaussian. But you look at it and you say, well, it doesn't look Gaussian because the level curves are not elliptical, but that's only if you're viewing it in X, Y, theta coordinates. In the Lie group setting, there's something called exponential coordinates. And so the rest of the title of this paper is the banana distribution is Gaussian in exponential coordinates, okay? And so we can fit that kind of distribution very well using this sort of Lie group mathematics. In contrast, the classical Kalman filtering usually uses X, Y, theta coordinates. So we get a better fit. And then what do we use this for? Well, one thing we use it for is robot team diagnosis and repair. So if you have a bunch of robots working together in a team, maybe they're painting, maybe they're carrying things, it doesn't really matter to us what their primary task is. What we want to do is endow teams of robots with greater robustness. So that means each robot is modular. It consists of, in this case, there are modules here. These are right and left wheel assemblies, the computer and battery, and then a gripper assembly. And they're connected together magnetically. And then the idea is that in the team, every so often, each robot does a little dance and the others watch it. And then they diagnose, is it performing the way it should be performing? Or are what they're observing characteristic of a fault state? And that's a statistical decision process, because even if it's working correctly, if the wheels slip a little bit, it's not exactly going to make a figure 8. Within some statistical parameters, the others need to decide, is it within reason functioning correctly, or is it more characteristic of a fault state? And so you can think that there's a little banana distribution propagated for each fault state. Like if the right wheel motor is burnt out and you tell it to do a figure 8, it'll just oscillate back and forth around that wheel. Or you can imagine various other fault states. So that's one place where we use this.
Mm-hmm. So can you go back to this slide? Are those robots purely are you computer science? Are we using the word decentralized? I mean, autonomously, or you have a centralized control?
So here, in this particular experiment, it was centralized and they pooled their information. But there's a lot of work on consensus, and so the part that we focused on was how to generate these individual PDF probability density functions. Here, they're all pooled together, but you could have a graph structure and just local neighbors talk to each other, and it could be decentralized. Yeah, but the sort of piece that we're adding is how to model the noise and put this together in a maximum likelihood framework. But yes, it could be decentralized, but back then, which is what, like more than 15 years ago, we didn't do it that way. Yeah. So again, we use a lot of mathematics. I'm not going to get into it, but it involves the concept of convolution. I know CNNs are very popular. The kind of convolution that we do involves both rotation and translation, and we develop fast transforms for these sorts of things, and do probability and statistics on Lie groups as well. And so these are some of the books. As I said, I brought one as a gift today. But now I want to get into the new work, which I'm very excited about, which actually, you'll see at the end of the talk, it draws on the same mathematics as the old work. And we're developing something we call the Spirit Dictionary, and I'll show what that means in a minute. It's all about affordance-based reasoning of objects. And so whereas my older papers all have fancy mathematical titles, my newer papers have kind of cute titles like, is that a chair? So a robot encounters an object and wants to answer the question, is that a chair? Okay, or put the bear on the chair. You'll see that one in a minute. And can I pour into it? If the robot comes to an object, is that object a container? So can it contain water, for example? So the whole idea of affordance-based reasoning, what we also call robot imagination, is what can a robot do when it comes to situations where there's no prior training? And so the idea that we have adopted is to use affordance-based reasoning about unknown objects. So of course, deep learning is very popular, big data, you have, ImageNet and millions of images of cats and cups and chairs and other things. And then in that space, interpolate, and you can say, okay, this is this or this is that based on appearance. But we want robots to function much more robustly in the real world. And there are robots in the real world. These are two robots. This was in a lobby of a hotel in China that I went to maybe 6 or 7 years ago. And one of them was cleaning the floor and one of them was greeting people. But they were cute, but they weren't very smart. So the cleaning robot had no idea that the greeting robot was there, right? So we want to develop smart robots, basically. and that can go beyond their training and beyond current information. So it's like what Einstein said, imagination is more important than knowledge, okay? Big data maybe leads to some kind of knowledge, but we want to go beyond. We want to look at imagination. Now, I'm not talking about like artificial consciousness or blah, 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 that kind of thing, okay? What I'm talking about is foresight of action before taking the action. So how can a robot have foresight of action? Well, we can build in a physics-based simulator. We can do real to sim transfer, put what is observed in the real world into the sim, have it play in the simulator, and then act, okay? So that's what we're really talking about, okay? So, and in Singapore, where I got a lot of money over 5 years to do elder care robotics, okay? So that was the motivating application because of the low birth rate, et cetera. How can we make robots smart enough and have the people have enough trust in them that you can leave them to take care of grandma, for example. And there's a lot of related work on affordance-based reasoning. We didn't invent this. It goes back to the 1970s. The psychologist J.J. Gibson was the sort of founder of the theory of affordances. And then it slowly has crept its way into the robotics literature. But we're doing it in a specialized way. What we're doing is we're building what we call the Spirit Dictionary. So this is a forced acronym. It's Spatial Information-Rich Interaction-Based Task Dictionary. So the idea is that if we have a dictionary of the functionality of common objects, then that can tie together many things, NLP, and knowledge representations and planning, et cetera. And so I'll illustrate with an example how this works. So we'll look at the example of a chair and of a cup. So the affordance-based definition of a chair. Well, what is a chair? A chair is something you can sit on. And what is the definition of a cup? Well, it's something that can contain liquid and you can drink from, okay? You can even cup your hands and then your hands become a cup, right? And so the appearance is not important. So this was a paper we published back in 2020. So chairs come in all kinds of different shapes. And you can do very well using deep learning, but this looks like a chair, but you can't sit on it because it's a dollhouse chair, right? And this looks like a chair, but it has no seat. Okay, so it's possible to fool in the interpolated space of all images things that appear to be something, but actually do not have the correct functionality. So then what is our scenario? The smart robot comes to an object and it asks itself, is that a chair? Well, it's not enough to say yes or no, it's a chair. It needs to know at what orientation that needs to be used to support the function of sitting. Because if it just answering the question, categorizing or classifying and saying, yes, that's a chair is not enough. It needs to be able to find out how to use that object as a chair. So what we do is it's real to sim to real. The robot comes, it scans the object, takes it and drops it in simulation at many different orientations, sees where it settles, and then drops a humanoid figure on it and sees if it supports sitting, okay? And then if it does, then it simultaneously has found it is a chair and that's the correct orientation. So the next slide is the one that everyone likes. Well, this is just dropping a different orientation. So it's using a physics engine, and actually it doesn't matter which one. We started out with what was it, PyBullet, and then we've moved on to IsaacSim, NVIDIA IsaacSim, but we're sort of agnostic to the particular engine, but this is showing the idea. So it's a multi-rigid body physics mechanics simulator. We're in the mechanical engineering department, so mechanics is a big thing. And then you can see that it finds that there's an orientation that you can drop this figure from that will support sitting when the chair is upright, but not when the chair is not upright. So then in robotics, we like to do demos. So this was the follow-on paper, put the bear on the chair. So the idea here is now it's doing the scanning. So this arm is only used for scanning. Then in the robot imagination, we're doing the so-called sitting imagination to assess sittability of the object. We like to invent our own words, sittability, containability. Well, I guess that's already a word, but anyway, and then we're integrating this with planning. Oh, I turned the volume off, but the robot is saying, I can't reach the chair that way, please turn it. This is a little robot human collaboration. And then the robot says, okay, I can now reach the chair. I've identified it is a chair. I've made a motion plan to go to the chair. Now I'm going to demonstrate for you that I understand it's really a chair. I'm going to seat the bear on it. So that's why the paper is called Put the Bear on the Chair, okay? And it looks like a very easy thing to do, except that the robot has many articulated degrees of freedom that have to be coordinated. The bear has passive degrees of freedom that have to be coordinated. And at the end of the day, you want the bear sitting in the chair. You don't want the bear falling off the chair or the robot clashing into the chair. So even just taking a few steps forward and bending over and putting the bear on the chair is actually somewhat of a challenging task in robotics, okay? And we're doing it with the bear first, and then we're gonna do it with grandma, well, let's say a few years later. And then after it's been tested with grandma, then maybe we do with baby, also, because childcare is another application. So you can see all these successes, all kinds of different chairs. Everything is previously unseen, okay? There's no database of chairs that we're using. We could use as a prior, but we're not relying on data, okay? Singapore is an island, if the robot finds itself on a tropical island, no link to the internet, it could still function as long as it has power, okay? So this is just showing all the wide variety of chairs. And then there's an example I really like coming up where we made a makeshift chair out of my books, okay? And maybe a deep learning thing might recognize this as like a bookshelf or a library or something. But in our approach, it can recognize it as a chair. So here, just keep an eye on this one over here. I have another project in Singapore where we were doing things with shipping containers because there's a port. So we made this makeshift chair out of shipping container models and a stack of my books, and it recognized that that could support the functionality of a chair. So, so that's put the bear on the chair. And then the following work is what we call prepare the chair for the bear.
So, sorry, I have a question.
Yeah.
How you can actually put the model of the chair into the simulation so that you can.
Yeah, so we're using depth cameras, and so we get that's actually, I'll show you this one. Is maybe more clear. So here the chair is upside down. The robot is scanning, constructing a point cloud of the bottom. Then it goes and it picks it up and it turns it upside down, and then it scans the top. Then it takes that point cloud, we develop a solid model. And actually later in the talk, I'll talk about this. We have some CVPR papers about fast construction of solid models from point clouds. And then we take that solid model and we put it into the physics-based simulator. I shouldn't say we, the robot puts it from its observations to its imagination. It does it, okay? So then it's then done the full scan, then it brings it over, and then it's the same as before. It's going to, it has to figure out how to place the chair so the other robot can reach, and then the other robot will put the bear on this chair. So, but first this chair had to be prepared for the bear. Okay, so prepare the chair for the bear. So our next paper coming up is going to be Goldilocks and the three beds. So, there's Goldilocks and the three bears, but it's we're going to focus on baby bear and three beds. This one's too hard, this one's too soft, this one's just right. So you get the idea here. So it successfully places the bear again. Okay. Then we had this other paper, Can I Pour Into It? And the idea here is that we have the robot encounters a cup and wants to use it as a cup. So this is a teaser of the end result. This is zero shot. there's no learning involved. It did the scan of the objects, put it in a pouring imagination scenario, and then it knows this cup that it was grabbing, but it didn't know any of those other containers. And first time it works, no training, because it's been training in its mind. It didn't have to do many experiments to calibrate. So again, how this works, the robot comes to this previously unseen object and queries, can I pour into it? Okay, so we need a simulation environment to simulate pouring. So what it does is, again, it's real to sim. It does the scan. In this case, you get this very rough model. This was before we did our CVPR work, where we have nice smooth models reconstructed from point clouds. Then we have a sheet of beads that we drop onto the object and see if beads are retained. If it looks like a cup but has a hole in the bottom, so things would fall through, then it doesn't have the functionality, so that would fail. So at the bottom here is like a roll of tape, so it rules that out as an open container. But the other one, beads are retained, so it is classified as an open container. And then there's simulation of actual pouring from different angles, and then it goes through and it does it.
Nice.
So here's like a half coconut looking thing. I mean, we were in tropical islands, Singapore, so it scans it and then gets the solid model. We put the solid model into the physics-based simulator. It then determines which beads fall in, and that beads do fall in and stay under some perturbation, so there's some stability. And then it calculates, well, what was the footprint, how many beads went in, what was the footprint of the beads that went in. So then a reasonable place to pour is the center of mass of this footprint. But then what speed, what angle, which direction, then it does those simulations. And then after it figures out the best one, then it goes and it does it in the real world. First time. No training, no big data, just imagination. Okay. Yeah.
How could the robot make sure all the edge keys he included in the simulation?
What do you mean by edge case?
You know, what kind of degree he have to try to pour in the cup, but how could now, okay, how many degree I should try to pour in the cup?
Well, in the end, it only needs to have one successful one. So there could be many edge cases where it almost pours in, or if it pours out and everything goes outside. But it's shooting for the center of that footprint, the center of mass, which is a good place to start. And then sort of perturbations around there. There are hyperparameters that we set, you know, but you know, we set it once and we don't change it for each new object.
So then the robot doesn't exactly find an optimal way to pour the water in. Instead, it uses a maybe you could say as a educated randomized guess to find a way to pour the water in.
Yeah, there's a set of pouring possible positions and orientations, and it tests those. And then there was a calculation we did here, which I won't go into, about the probability of success, et cetera. I don't say that it's the global optimal, but when in the middle of the night when I'm thirsty and I go to the refrigerator and I pour, I don't think I'm doing it optimally either. Yeah.
So then on average, how long does it take for the robot to build the unseen object to actually performing the pouring action?
So it depends on how many processors you parallelize to, because all of these trials could be on a different processor, right? But on we had 4 graphics cards, and you know, we're talking minutes.
Okay.
So it's not hours, but it's not instantaneous either. And so, but you know what? I think the biggest problem in robotics, though, is the robotics hardware. So as the robotics hardware gets good enough that this could be used in practice, the computing power will go so high that I expect the time to be reasonable by the time we'd be ready to deploy in the real world.
Oh, thank you.
Yeah, so we saw this already. And then we did a study of all different kinds of open containers and non-containers. And it classified very well, like 96% accuracy, and for previously unseen objects. Okay, of course, if we use a prior like Affordance net or ImageNet, we can, if we use a prior, we can get even better. But actually, we were competing against to show that ours did well without any prior knowledge. And then here's just some other examples of the simulations. And then going to the real world, I'll say there was this, we actually did better on previously unseen objects than other learning-based methods. And so sort of more of the same, and then again, zero shot pouring successfully. Now that doesn't mean that we were always successful. And so I'll show you an edge case in a moment, where there's a vase with a narrow neck, and in simulation, the algorithm claimed that it could be poured into, but here, when you pour into it, all the beads bounce off, okay? So there's no 100%, but 98% is not too bad. And even some counterintuitive things like the robot could determine that it could pour into the moat of this candlestick successfully. So is that a cup? Well, you may look at it and say, no, it's a candlestick, but from an affordance-based perspective, if you're thirsty enough, you could pour into the moat of the candlestick and drink from it, right? Okay, so now back to some science. We do quite a lot of convex geometry and robot motion planning. And so these were a bunch of papers that we've published over the years related to Minkowski sums and configuration space obstacles and things that people in the computer science side of robotics look at. And so for those of you who don't know what a Minkowski sum is, basically if you have one object and it's fixed and you think of another object that's moving, and when will these collide? Okay, well, they'll collide when there's at least one point of contact. And if you think of all the possible ways that the moving body can move around and remain in contact without intersecting with the fixed body, that traces out a boundary which is bigger than the original object. And that essentially that's the Minkowski sum of the two bodies. And that tells us if we were to take the moving robot and shrink it to a point, then that tells us where the boundary of that point can go without colliding. So that's a configuration space obstacle. And we came up with a very handy formula to say, if you can parameterize body one by its unit normal direction, and you can parameterize body two by its unit normal direction, then the Minkowski sum is just the sum of those two things, which is a new result in convex geometry. And so then we can have a closed form description of that boundary. And then if we want to do motion planning, then all we have to do is like an onion with layers. We can parameterize layers outside of that boundary and look in the free space instead of doing sampling, collision detection, throwing away, and etc. So that was one thing we did, and I'll show some results in motion planning in a moment. And then the CVPR work that we did was about taking point clouds and fitting unions of simple superquadric surfaces. So like if you have a point cloud for a lamp here, then the lampshade, the stem, and the base are three pieces that are each convex bodies. So we have a unified framework for capturing the sense data, making solid models, putting those solid models in physics-based simulators, as well as in motion planning. because if each of the pieces is convex, we can use the formula that I showed previously, and then we can do this for human figures as well. So our algorithm is the one in the middle here, I think, and comparing to some other algorithms on the right side. So in each, it's sets of three, the point cloud, ours, and then the standard. So in robot motion planning, the big problem is cluttered environments. So there are algorithms developed primarily by computer scientists, the probabilistic roadmap, PRM, or RRT, rapidly expanding random trees, that are very popular, and they work very, very well, except in narrow passages when there's not much room for the robot to move. If there's open free space and a few obstacles and a lot of room to move, those methods already work well. But in this case down here, where you have a narrow passage and it has to make its way through, the problem with those existing sample-based methods is that there's a lot of sampling and rejection going on. And most of the time is spent on rejection, okay? And so in our approach, we're basically parameterizing the free space with this Minkowski sum idea. So here, the green part is the free space, and we can parameterize it and just sample from free space and not do a lot of collision detection and throwing away. So we sample the free space, we get medial lines in the free space, and then have the planning done. When I talk about the Minkowski sum, that's when the moving body is at a fixed orientation. So for each different orientation of the moving body, you get a different Minkowski sum. So that can be considered to be a slice of the configuration space at a fixed orientation. And then those slices for different orientations need to be added up. And then you need to go between those slices also to do motion planning. So that's what we've done. And we published just last year on that. And here's some examples of, my videos don't want to play. Okay, so having an articulated multi-degree of freedom, let's say robot made of a union of convex bodies, and then you have the obstacle field, which is also a union of convex bodies. And it works quite well. And then the final topic I'm going to get to kind of ties in all of these things together. The old work on the workspace density, together with the robot motion planning and the Lie groups and all of these things. And this is an affordance, what we call affordance learning. And the particular method is called PRIMP. And this paper is in review. Actually, I think we have the archive version up on the web. And the idea is, it's a kind of learning from demonstration. But the learning is that it's being performed from the demonstration is about the functionality of things. So here's a video that shows it. So here is a scooping task. So here on the upper right is the demonstration of scooping in one bowl by a human user demonstrating. Then the robot scans a new bowl, which it's never seen before, and does the robot imagination, the physics-based reasoning of scooping. And then it looks to see how can I reach, but the thing here is in the real world, there's this robot sitting here, which is an obstacle. So it was trained without obstacles, and it was trained on a different bowl and scooping a different material. And here's pouring also, scooping and pouring. But then when you have obstacles in the way and the bowl is different, so that you have to assess how to pour into that bowl or scoop from that bowl, those are like the boundary conditions or the end conditions for a probabilistic motion planning. That's what the PRIMP method is about. So here, I like to use my books as obstacles, and it's able to do the job. Other things like opening drawers or doors, we're applying this there as well. So So we're not doing much learning, although I do. So I have some papers on learning. I have other papers where the title is a learning-free method of doing such and such a thing, right? Because learning is great, but it's not the only way of doing things. And we want to demonstrate what can be done first with this imagination framework on its own, but then of course combine it with knowledge from learning as a prior in the future. So here's doors and drawers, because again, the motivating application was household robotics, particularly for elder care and hospital care in Singapore. Now here, so because I'm here now, so that's pretty much all I wanted to talk about today. So just to review, we have a bunch of old topics, brand new topics on affordance-based reasoning, and we're developing this spirit dictionary. We're now actually combining with LLMs. So instead of hard coding simulation environments, we're writing, scripts and then having movies generated by generative models, and then have those linked to the physics-based simulation so that we can bootstrap up and get, develop this dictionary very, very quickly rather than hard coding each household object functionality separately. And so we have a lot more cute titles. We just had a paper come out called I Get the Hang of It, where the robot has to put a hanger on a hook. And that's also without, and it can put cups on a mug tree for drying and other things. Another one we just submitted actually today on how to put lids on containers, right? So the title of that is put a lid on it. So anyway, we're continuing along these lines, bringing in science with sort of cute demos and doing motion planning and all kinds of other work, and happy to talk to folks about collaboration. In the Lee Group side of things, we do a lot with fast algorithms, extensions of FFT, wavelet, things like that. And yeah, so I'd be happy to take any questions or talk about collaborations.
What do you think? Is this like a really eye-opening talk? I don't know how you feel, but I feel like this is the most eye-opening talk I sitting here. That's here. It's really cool. But I will let our students ask you a question first.
Any questions?
Yeah.
So my question, you can see. Okay, okay. I think the topic is very interesting, especially the Minkowski-sum planning. So I used to do some similar work, narrow space plan, motion planning. And I was wondering, so after you building those different layers, do you use a search method, search on such big space, or you use some optimization method to search a path between those layers?
So what we're doing is we're developing a highway system, a skeletal medial axis system, so that the dimension of the space is manageable. So we get so basically we develop, if there's, let's say, two C-space obstacles, we generate a path in the middle of them, and we have a graph basically. So that part is similar to what other people do in terms of decompositions of free space. But the novelty of our approach is that we can parameterize free space rather than doing collision detection, throwing away, and because that's what chews up a lot of time and makes PRM and RRT methods expensive in narrow passage problems.
So in your defined free space is not necessary to be convex. It can be concave.
Well, the obstacle and the robot component have to be convex for this formula that I showed to work. But if you can decompose a non-convex body into a union of convex ones, then we can still do it.
Okay, thank you.
Yes, please. Thank you for your talk. It was focused very much on robotics. That seems to be your area given mechanical engineering. I was wondering, do you know for the Lie group state estimation and the various algorithms you mentioned, do you know of other applications, say to like function approximation or
Function
machine learning?
approximation. So the state estimation is for essentially the kinematic or dynamic state of some object or system. So it doesn't have to be a robot, it could be, you know, an airplane or a satellite, but something moving in 3D. I'm not sure when you say applied to function approximation.
So like if you were going to, so essentially it's based on something like rational function approximation
Okay,
has some similarities to like a Lie group if you kind of squinted it.
okay.
So I was wondering if you could like maybe if you were going to do something like, this is off topic, I was just wondering about applications, but this was an idea that I had. I was wondering if you were looking at like an online, as you introduce data to the function you're trying to approximate, could you model that as like a dynamic system and then do something with this kinematics? in that sense?
So when you say function approximation, like a pade approximation or something, or when you say function, do you mean like y equals f of x, in approximating f of x, or do you mean like function in some other
I was
sense of the
thinking
word?
AAA algorithm specifically, rather than the pade approximation, but.
Okay, but it is to approximate a function
Yes,
f of x.
So like if you were introducing additional observations of your function, could you treat that as like a dynamical system
Uh-huh.
of some sort? And then
It could be, I mean, the Lie group approach that we're taking is more it's focused on sort of rotations, rigid body displacements, so those sort of specific Lie groups, maybe unitary matrices. There's one infinite dimensional Lie group we look at, which is reparametrization of functions. So if you have functions from 0 to 1 into 0 to 1 that are monotonic, and you compose such functions, they're also of the same class. And so, but that's actually an infinite dimensional group. And then you can ask the question, for example, if you have a trajectory, how should you reparameterize it so that you're moving as uniformly as possible? I mean, if you're on a straight line segment and that's easy, you have even tick marks. But if you're rounding a corner sharply and then you have a straightaway, maybe you want to sample more at the roundabout and use fewer samples on the straight part. And that's related to like CAD CAM kind of things. Whether you call that robotics or not, I don't know. But so I had a paper on that as well, on using variational calculus and finding the optimal reparameterization. But I'm happy to discuss and learn more about what you have in mind.
Well, I have a question. Can I ask? Okay, so I really like what you said, imagination. I think that's, computer science right now is just so, I don't know how to describe that, but it's big data.
It's all big data.
You're collecting data and then you use it to learn this stuff. But I think those ancient stuff and then how you're gonna handle this. This is really cool. So when you guys submit paper to CVPR, because you are using very different approach.
Yes.
Right, so the CVPR guy, most of them is trying to learn from ImageNet. Actually, ImageNet author was also here before.
Oh, wow.
Yeah, Jardin from Princeton.
Uh-huh.
Yeah, he was here last semester. So I think that that's a traditional computer science approach, but you guys are doing things, I think it's this. So when you submit a paper to CVPR, did you sometimes getting the people, if unfortunately some people don't believe this and they will reject the papers?
It happens, but we were lucky. We submitted 2 papers to CVPR, and the first one got oral presentation.
I know, last.
And then the second one got highlighted presentation. So they were accepted, and because it's different, some
Maybe they like it.
they like it.
Yeah.
Because it's different and it's double blind, so they don't know we're mechanical engineers.
Well, speak of that, I want to tell you guys, Greg was, before he joined the UD, is really, for us, is a great, it's our very fortunate to have him join us because, and his leadership in US, National University of Singapore, mechanical engineering now is ranking globally number 9. It's really a top. Yeah, I think it's the top in Asia right now, right?
It goes, Tsinghua, Peking, and then they
Yeah,
switch roles, yeah.
Yeah, so it's great. So if any of you are interested in working on this CVPR, like these things, if you can, think about inviting him to serve on your PhD committee and etc. So I'm sure he might be very happy to do that, just to share with this with you.
And we are doing LLM work now too, so, it's not developing LLM, but using it to develop the robot imagination work.
Yeah, speak of that, last time when I was at MIT, I saw there was a presentation from MIT, one of, probably also from mechanical engineer. The PhD students using LLM to design all the experiments in there. So they are using this much advanced, sounds like they are all computer scientists. So it's cool. So I found that they already have papers published in this very top, like I forgot. It's one of these, like, not in Nature, but it's somewhere.
Oh,
else.
yeah.
It's cool. Yeah. Okay.
Okay, well, thank you.
Thank you so much. Yeah.
Yes, that would be all for this. Thank you, everyone.